In the first part of the presentation, I gave you an overview of how ultrasonic systems work. In the second part, I will focus on some specific topics and go into more details. First, I will discuss the internal structures that our software uses for sequencing. There are three main data structures in our software that deal with the sequencing. These are the shoot table, the focus table, and the ray line table. The software fills these tables with suitable entries depending on the imaging mode that is used and the imaging parameters specified. The first of these tables, or the shoot table, deals with the properties of the transmits. When designing a new sequence, we would figure out all the different types of transmits that we need for the sequence and put them in the shoot table. The shoot table therefore acts as a database of all the transmits that are used in a sequence. Each row in this table corresponds to a different transmit item. The rows are indexed by TXID, which is the way other databases can refer to the items in this database. The different columns are filled with the properties of the transmit. Some of these properties include the beam's center element, the steering angle of the beam, the focus distance, half the aperture size, sound velocity, transmit frequency, pulse shape, etc. Just as a simple example, when we are doing B-mode imaging with 128 scan lines, our shoot table may consist of 128 rows for the 128 shoots, which are identical in almost every aspect except for their center element. The corresponding table for receive is called the focus table. Again, when we design a new sequence, we would figure out all the different types of receive that we need for the sequence and put them in the focus table. The focus table acts as a database of all the receives that are used in a sequence. Each row in this table corresponds to a different receive item. The rows are indexed by RxID, which is the way other databases can refer to the items in this database. The different columns are filled with the properties of the receive. Some of these include the beam's center element, the steering angle of the beam, the maximum distance for which dynamic receive focusing will be applied, half the aperture size, sound velocity, etc. Following up on our simple example from the previous slide, when we are doing B-mode imaging with 128 scan lines, our focus table may consist of 128 rows for the 128 receives, which are identical in almost every aspect except for their center element. The third important table which is used for sequencing is the ray line table. The ray line table deals with the order in which the transmits and receives are carried out and their timing. Each row in this table references one transmit item from the shoot table by its TXID and one receive item from the focus table by its RxID. The sequencer goes over the ray line table row by row, performs the transmit and receive, and moves on to the next row. The columns of the ray line table mainly deal with the timing of the transmit and receive. You will learn more about these parameters in the next slide. It is important to emphasize that our sequencer always performs a single transmit and a single receive. It is not possible, for instance, to do multiple transmits and then do a receive. Although it is possible to associate dummy receives to some transmits, the receives should be there even if they are of zero duration. Going back to our simple example from previous slides, when we are doing B-mode imaging with 128 scan lines, our ray line table may consist of 128 rows which constitute the 128 scan lines in the sequence. The TXID and RxIDs for these lines will be 0 to 127, corresponding to the shoots and receives that we put earlier in our shoot table and focus table. This is the timing diagram of our sequencer. The clock on most of our systems is a 40 MHz clock. That's the first signal in the diagram. The second signal is the start or sync signal. The sequencer can be synchronized with an external trigger source. The external trigger source can either trigger one frame, which is one cycle of all the rows in the ray line table, or it can trigger each scan line individually. This would be a single row from the ray line table. If the external trigger is used to trigger each scan line, then the second signal in this diagram is that trigger signal. If not, then the sequencer will generate the start signal for the next line in the sequence automatically. In this case, the line duration parameter from the ray line table determines the timing of the start signal. For each scan line, the sequencer waits for an amount of time equal to its line duration before starting the next scan line. The third signal in the diagram is the transmit pulse. The sequencer waits a time equal to the TBS parameter before it starts the transmission. The transmission will always correspond to 96 clocks of the base frequency, even if the pulse shape is shorter than that. There is no way for the hardware to know how many characters are programmed through the software. It kind of pads the pulse shape with zeros to fill the 96 character length and transmits all the 96 characters. The next signal determines when the hardware should start applying the dynamic receive beamforming delays to the received RX signals from different channels. The sequencer will wait 88 clock cycles plus the time determined by TBDL before it starts the dynamic receive beamforming. This instance in time should ideally correspond to the minimum depth for which the dynamic receive focus delays were computed by the software. The next signal, RX channel enable, commands the transmit receive switches to switch from transmit to receive mode. The sequencer waits a time equal to T inhibit from the start signal before it switches from transmit to receive mode. The next signal, RX, determines the duration for which the RF samples should be saved and transferred to the memory. The sequencer waits a time equal to TB save before it starts recording the samples. It then records the number of samples required and then stops recording until the next scan line's RX signal appears. The last signal was used in earlier versions when the envelope detection was carried out in the hardware and is now deprecated. This slide concludes my discussion of the internal structures used for sequencing in the Sonix platforms. In the next couple of slides, I will go over the block diagrams of the signal processing pipelines for different imaging modes. I start by the pipeline for B-mode imaging. Note that these pipelines correspond to version 6.x of our software. The 5.7.x and prior versions did the envelope detection inside the hardware. You can find more historical data about these systems on Wikisonix. The Ultrasonix hardware acquires beamformed RF data and transfers them to the memory of the PC. All the other processing steps are carried out by the Ultrasonix software inside the CPU. To form the IQ data from the RF data is multiplied by exponential of -j omega t, where omega, which is the center frequency, is a function of depth. Because higher frequencies are attenuated more than lower frequencies, the center frequency of the RF signal shifts downwards for higher depth. That's why we use a sliding frequency for IQ demodulation. After the demodulation, the signal is low-pass filtered to reduce the noise and prevent aliasing from downsampling. Then it is downsampled by a decimation factor. These steps constitute the IQ demodulation. The result is an IQ signal pair which is in the baseband. The next block is the envelope detection. To determine the envelope of the signal, we take the square root of I squared plus Q squared. This will result in a pre-compression 16-bit accuracy B-mode image. To reduce the dynamic range of this signal and fit it into the 256 valued grayscale range, which can better be perceived by the human eye, low compression is applied. We also reject the values below a certain threshold to suppress noise. For more information on the compression table parameters, please visit Wikisonics. The B-mode image is then scan converted. This is an interpolation step to map the data geometry to the actual geometry of the imaging plane, which is mainly determined by the geometric parameters of the transducer. Next, a speckle reduction algorithm is used to enhance the appearance of the image and reduce the speckles. Finally, gamma correction and color mapping is applied for displaying the images. Harmonic imaging is a method for acquiring enhanced B-mode images. There are two types of harmonic imaging: the tissue harmonics imaging or THI and pulse inversion harmonics or PIH. The pipeline for THI is similar to conventional ultrasound B-mode imaging. The only difference is that in the IQ demodulation block, the sliding frequency of exponential of minus j omega t is not the same as the frequency of the transmitted pulse, but it is a multiple of it. Usually the second harmonic is investigated. In this case, the frequency would be double the transmitted frequency. The other processing steps are the same as conventional B-mode imaging. In PIH, the sequence is slightly different from the conventional B-mode imaging. In order to form each RF line, two scan lines are acquired from each location with inverted pulse shapes. The received RF data for the two lines are then summed up. This cancels the main frequency component of the signal but doubles the second harmonic component. Since the second harmonic gets attenuated more strongly at deeper tissue, it is possible to use a depth-dependent weight factor for adding up the two RF data. The resulting RF data is then passed through the same pipeline as THI to determine the second harmonic and generate the harmonic image. Note that harmonic images are usually based on weaker signals and have a lower signal-to-noise ratio than conventional B-mode images. Therefore, we always mix the harmonic images with conventional images to get the desired image quality. In pulse wave Doppler, the RF data from the gate is first IQ demodulated. After that, it is passed through the wall filter, which is essentially a high-pass filter. This takes out the low-frequency components of the spectrum, which correspond to slow motions due to the operator or patient's movements. The resulting IQ data is then windowed and passed through the fast Fourier transform to generate the Doppler spectrum. The forward and backward flow components of the IQ are separated before generating the audio signal for the speaker. In color Doppler, the RF data from the ensembles is passed through IQ demodulation and the wall filter similar to pulse wave Doppler. However, since the ensemble usually consists of a few samples, for instance 16 samples, the FFT would not create a good estimate of the blood flow with enough resolution. Therefore, autocorrelation is used for blood flow estimation with the color RF data. In elastography, we do not use the IQ demodulation. The RF data from each frame is compared to the RF data from the previous frame, which was stored in a buffer. 1D normalized cross-correlation is used to track the tissue motion at different depths along the RF line. The estimated motion is then passed through the strain estimation block. This block takes the 1D spatial derivative of the motion by a least squares algorithm. The computed strain is then averaged over a number of frames and color-coded for display. A feedback is also given to the user on the strain quality based on the average correlation between successive RF frames. This slide concludes my discussion of our signal processing pipelines.